Welcome to the probability class. In the last session, we discussed about random variables and in particular discussed discrete random variable in detail. In today's session, we will cover the other type, that is continuous random variables. Let me bring out the PPT first. Here it is, continuous random variables. That's the topic for today. We have seen there are two types of random variables, discrete, whose ranges are whose ranges don't contain any interval of real numbers. It may be, this is the real number line, or discrete means it takes values at some discrete points. And we have seen examples where this number of points may be infinite. Still, it does not contain any interval of the real line. On the other hand, continuous random variables are those whose range covers some interval of real numbers. Here are some examples of continuous type. Waiting time to get a bus. You are standing at the bus stop and you are measuring the duration of time that you need to wait for the bus. That's a continuous random variable because it may take any value from 0 to, say, if you say that I won't wait more than, say, 1 hour, maybe 0 to 1 hour, anything. Okay. So it's not that it will take only discrete values like 0.1, 0.2, 0.3, etc. It can take values in the continuous spectrum. Similarly, height of a randomly selected person. You select a person randomly and then measure the height. Again, it's a continuous type. So is the response time of a website. You click the button of a website and then the duration of time that you need to wait for the response, that's the response time. Again, it's a continuous random variable. And each time you try to access the website, the answer will be different. So that's why it's a random variable. Lifespan of an electric bulb. Another example. Amount of national wheat harvest in an year or in a year. Again, that's a continuous random variable. Say you might measure in metric tons. So how many millions of metric tons you are getting in a year? So that's a continuous random variable. And each year you will be getting one value. Similarly, average rainfall during a year. That's also a continuous random variable. Now, let's talk about probability density function. It's a particular type of function, real valued function from the real line. When we talk about functions also, although we did not mention explicitly, but whenever we talk about function, it is always from a set A to a set B. We just did not mention these things explicitly so that the things don't get cluttered and so that the things don't sound too mathematical. But always in the background, whenever you talk about a function, it's from one set A to another set B. Say here is a set A and here is a set B. function f is a mapping from set A to set B. That means every element in the set A is mapped to exactly one element in set B. It may be so that more than one element is being mapped to the same thing. That's possible, but always one element here is mapped to exactly one element in B. That's the definition of function. And when we talk about this kind of functions, here our set A is also real number line and set B is also real number line. In other words, f is a function from R to R. That's what it is. So here you have got one, excuse me for a moment. Okay. Now we are talking about one particular type of function, and we'll call that probability density function, or in short, PDF, provided it satisfies the following two things. Number one, the function should be non-negative, that is, if x is greater than or equal to 0 for all real numbers x. So if 1 should be greater than or equal to 0, f of -5 should be greater than or equal to 0, f of -√3 should be greater than or equal to 0. If think of any number x, fx should be greater than or equal to 0. Now, what does property 2 tell you? It says when you integrate the function from -infinity to infinity, you get 1. Suppose this is the graph of f. This is the graph of the function fx. Here is x. This side is fx. What does this integration mean? Interpretation of this integration is the area under the graph of fx, because we know integration a to b fx dx is area under the graph of fx from a to b. So this means if this is the function, here is a, here is b, this integration means this area, right? This area can be calculated by this integration. So when we talk about this integration, it means the area under the graph from -infinity to infinity, and that should be equal to 1. That's what the second property tells us. So if a function f satisfies these two conditions, then we'll call such a function a probability density function. Remember what was probability mass function? There we had some points x1, x2, etc. Excuse me. The first criteria was as it was in the case of probability mass function, and over there we had a discrete set of numbers x1, x2, etc., such that summation of fxi is equal to 1. That summation, because there we had discrete points x1, x2, etc., here we don't have discrete points. So we are replacing that summation by the integration. That's the difference. We know what is meant by random variable, what is meant by continuous random variable. In particular, we know that thing. There is a random experiment in the background, and that random experiment, this is the random experiment, and each time we perform the random experiment, we get a value of x. And suppose this is a continuous random variable. Okay. We also know by the previous slide what is probability density function. And there are lots of probability density function, not only one. You will see lots of examples later. Now, we are connecting now random variables with probability density function. We are going to connect them. We say, look at the definition. We say function fx is the probability density function of x. We are connecting random variable x with a probability density function, or PDF in short, f. We are connecting them. So we say fx is the probability density function of x if it satisfies the following two conditions. Number one, fx is a probability density function. And we already know what is the meaning of that. So fx is a probability density function. And number two, this is the connection. Property number one, see, property number one is an independent property of small f. It does not require any connection with the random variable x. The second one tries to connect the random variable capital X with small f. How? That's what it says. Probability of A less than or equal to X less than or equal to B. That means this thing is given by the integration of fx dx from A to B. That means it is given by the area under the graph fx from A to B. This is important. And that should happen for any two real numbers A and B satisfying this. So here is the real number system. Here is A, here is B. And if you try to compute probability of A less than or equal to X less than or equal to B, then all you need to do is integrate this function from A to B. That is, if you know how much is the area under the graph from A to B, then you are through. So you see how easy it becomes if you know the probability density function of a random variable to calculate different probabilities. In a sense, it gives the probability mapping. That is, where is how much probability for the random variable x distributed over the whole real line. It gives you a map. What does the geographical map tell you? Say, it tells you, it gives you a sense where are different places, which place appears on the east, north, south, etc., with respect to certain position. That's what you are getting here. You are getting the overall probabilistic picture so far this random variable capital X is concerned. Let's go to the next slide. Now, what are the properties of PDF or probability probability density function? Suppose X is a continuous random variable and small fx is its PDF. Let A and B be any two real numbers satisfying, as earlier, A less than or equal to B. In other words, you are fixing a picture like this. A is less than or equal to B. A may be equal to B also, in which case they are identically the same point. So interval is of length 0 in so this interval A to B. How much is the length of this interval? This interval has length B minus A. And if B equal to A, then this becomes 0. So you have random variable capital X and this one. Then the following conditions hold good. What are the conditions? Number one, probability of capital X taking any particular value A is 0. This is extremely important. This is the real number system. Take any number A, probability that X takes precisely that value A, that is nothing but 0. That's very surprising. How can it be 0? because overall probability is 1. How can it be equal to 0? The thing is, here, although capital X takes any specific value A equal to with probability 0, but probability is spread over the line. So whenever you talk about any interval, probability of X taking value in the interval may be positive, maybe 0, but it may be positive. And how can it happen? Because there are too many numbers here. I'm trying to avoid mathematical terms. Here there are uncountably many points, actually. Not only infinitely many points in an interval, because you may argue that if I add infinitely many zeros, still I should get 0, right? So probability of an interval should be 0 in that way. But no, an interval has got infinitely many points, that's true, but more than that, it has got infinitely many points, but too many of them. In a nutshell, if I need to say. That's why when you talk about the probability of a random variable lying in an interval, that is probability of A less than or equal to X less than or equal to B, you may still get positive values, although this thing happens. This is an important condition. And why does it happen? Let's see. Why does it happen? Probability of X equal to A, that is what? Remember the definition of PDF of a random variable capital X? It is nothing but, I can rewrite this event as, let me take space here. I'm now elaborating this thing. Probability of, I'm writing this thing here. X equal to A, I can rewrite that event as A less than or equal to X less than or equal to A. This event and this event, forget about the P part, P means probability, but event-wise, these two events are same. And by the definition of PDF of a random variable capital X, we know this must be equal to integration of A to A fx dx. And when we integrate the function fx from A to A, how much is the area under the graph of fx from A to A? That must be equal to 0, because we are just talking about the area of the graph from A to A. That must be equal to 0. That's why this is 0. Now look at these things. Often, of course, we need to calculate this type of interval. By the way, how many intervals are there of this type? Say, I mean, here is the number A, here is the number B. There are 4 intervals, right? Both closed. By the way, what is the meaning of this interval? All the numbers such that, this means all the numbers such that A less than or equal to X less than or equal to B. That is, it includes the end parts. What is the meaning of open interval A to B? It means X such that A less than X less than B, right? And similarly, A, B, right closed, left open, and left closed, right open. There are 4 types. Both endpoints may be closed or open. That way you get 4 intervals. So although we know how to calculate the probability of this type from the definition itself, we don't know how to calculate the other 3 types. So this property talks about calculation of the other 3 types. In fact, they are all same. Why is it so? Let's see why all these 4 probabilities will be same as this integration. Let's see why is it so. What is the difference between this event and this event? Keep aside the probability part. Think about the events. Let me write it down here. The event A less than or equal to X less than or equal to B, that is nothing but A less than X less than or equal to B, this event union with the event X equal to A, right? I can write this way. Now these two events, this event and this event, are mutually exclusive, because if capital X equal to A, at the same time capital X cannot be greater than A. So probability, when I take probability of this event, that will split into two probabilities, with this thing probabilities being added up, right? Plus probability of this thing. And by virtue of the first property, this is nothing but 0. That's why this probability is same as this probability. And similarly, this thing also, by observing that probability of X equal to B is equal to 0. And when you take both the points, then you get probability of A less than capital X less than capital small b is also same as this thing. Do that thing. Convince yourself that this is also equal to this. And that's why all these four are same as integration of A to B fx dx. How about this? 3. By the way, these two things should be same. That should be clear by now, because probability of capital X equal to A is equal to 0. Let me tell it properly. Probability of capital X equal to A is equal to 0. We know that thing. That's why this is equal to this thing. Now, why is this same as this integration? Now, what does the event X greater than A mean? Here is the real line. Here is A somewhere on the real number system. And you are talking about the event X lying on the right hand side of A. So that should be the area under the graph from A to infinity, because this event X greater than A, event X greater than A is nothing but A less than X less than infinity. Right? I can rewrite this thing. And although we have only for finite numbers A to B that property, that probability of A less than or equal to X less than or equal to B is equal to integration A to B fx dx. We have this property, but that property can be easily extended to this thing, to infinite intervals also. I'm not getting into that mathematical part, but one can do that thing. And all you need to remember is this is valid here also. So let me summarize. Probability of X greater than A is nothing but X lies in the interval A to infinity. And that's why we can write this as integration A to infinity fx dx. Similarly, probability of X less than or equal to A is same as probability of X less than A, and both the things mean the area of the graph from minus infinity up to A of fx, of the graph of fx. Let's check which of the following examples are PDF and which are not. Okay. So what are the two properties that fx should satisfy? Let's get that thing. These are the two properties. Sorry, not this one. This is the definition of probability density function. Number 1, fx should be greater than or equal to 0 for all real numbers x. And number 2, integration of the function from minus infinity to infinity must produce 1. Let's see each of the given examples and validate whether the two given properties are satisfied or not. Fx equal to x. See, f of 3 equal to 3, that is of course greater than 0. How about f of minus 3? That is minus 3 and that is less than 0. So the first property is violated. That's why this is not an example. This is not an example, right? And the reason is f of minus 3 is negative. Similarly, there are a lot many other values of x for which fx is negative, but we need only one. As long as you get fx is negative for 1, you know it cannot be a PDF. How about this? Let me draw the function of the graph. Something like this. X, fx, and this is the graph of mod x. Then area under the graph, as you can see, means when you this part as well as this part, and this is obviously both parts are infinity. They are not finite numbers. It's quite obvious. But anyway, anyhow, just to do it mathematically, let's check that this thing minus infinity to infinity fx dx is actually greater than 1. That will be enough. Because fx is non-negative, minus infinity to infinity fx dx must be greater than 0 to 8, say for example, fx dx. Because the greater than or equal to this thing. Because fx is non-negative. So when we do the integration minus infinity to infinity, in other words, when we measure the area, total area, when we measure the total area under fx, that area must be greater than or equal to the area from 0 to 8. Because fx is non-negative. Now let's measure how much is the area from 0 to 8. Here is 8. 0 to 8, this area is, so this is the function mod x. This side length is 8. This side length is also, this is a triangle. First of all, this is a triangle. And this side length is also 8. So how much is the area? This is half into base into height. And that is equal to 32. So this area is greater than 32. So obviously, integration minus infinity to infinity fx dx is greater than 32. So it can never be equal to 1. That's why the second condition is violated here. The second condition, that is integration from minus infinity to infinity, must be equal to 1. That condition is violated here in case of example 2. So example 2 is also not an example. How about this? Here is 1. And the graph of the function, look at the graph of the function. Between 0 and 1, it is 1. Otherwise, it is 0. So the graph is this bold line. This bold line is the graph. Obviously, fx is greater than or equal to 0 for all x. This is the symbol for all x, right? For all x real numbers. How about the area under the graph? Or how about this integration? Let's split the integration into 3 components. Minus infinity to 0 fx dx plus 0 to 1 fx dx plus 1 to infinity fx dx. Look at the definition of fx. When x doesn't lie in the interval 0 to 1, fx equal to 0. And the way we have split the integration, this integration turns out to be 0. And so does this integration. Both these integral values must be equal to 0 due to the definition of fx. So only remaining thing is the middle integral, 0 to 1 fx dx. And in this range, 0 to 1, what is the value of fx? 0 to 1, in this range, fx is nothing but 1. So it turns out to be integration 0 to 1 dx, that is x 0 to 1, and you get 1 minus 0 equal to 1. So this example is one of a PDF because it satisfies both the conditions 1 and 2 of probability density function. So here is a valid probability density function. So these are no, but this is yes. How about this function? This function, let's check. Again, it's easy to check that fx is greater than or equal to 0 for all x. That's true. For all x. How about the integration? How about the integration? 0 to infinity fx dx. That, minus infinity to, I will have to take the integration minus infinity to infinity. But that turns out to be only 0 to infinity fx dx, because when x is negative, fx is 0. So only part that matters to us is 0 to infinity. And over there, what is the value of the integrand fx? That is e to the power minus x. And you can do it two ways. More formally, you can do this way, limit of r tending to infinity minus of e to the power minus x 0 to r, and that gives you limit r tending to infinity minus of e to the power minus r plus 1, and you know e to the power minus r, this quantity goes to 0 as r tends to infinity, because exponential of a large number turns out to be exponential of a large negative number turns out to be extremely small, and it gets smaller and smaller as capital R tends to infinity. That's why this term goes to 0, this term, and the whole thing goes to 1. That's why we get this thing equal to 1. That's the more mathematical way of doing this thing, but sometimes we do a quick dirty way. So then it turns out to be 0 to infinity e to the power minus x dx is equal to minus of e to the power minus x 0 to infinity. And when you put x equal to it turns out to be e to the power minus infinity. Although, please understand, this is not a mathematical way of writing, but intuitively sometimes you do a quick and dirty thing, that plus e to the power minus 0. So then this turns out to be, this is nothing but the meaning of limit of this thing, r tending to infinity e to the power minus r. This is same as this thing, and that is 0. But intuitively you may say that this is equal to, because we know that for large negative numbers, e to the power, that number is very small, this is equal to 0. Okay, so then you get e to the power minus 0 equal to 1. Whatever, we have got that this is also a valid probability density function. How about this? Let's check this. Again, fx non-negative is easy to check. How about this integration? Minus infinity to infinity fx dx, and fx here is 1 upon pi into 1 by 1 plus x squared dx, and that is nothing but 1 by pi again you may do say you can do it mathematically, of course, more elaborately, but if I try to save time and do it quickly, then this is first of all this is equal to 1 by pi and this is nothing but 1 by pi. What is the integration of dx by 1 plus x squared? That is tan inverse of x. And this is, again, we are doing a quick dirty way. And that is 1 by pi. This is pi by 2 minus of minus pi by 2. You get pi by 2 minus of minus pi by 2. So 1 by pi, this thing turns out to be pi, and that's why equal to 1. However, you may do it more formally by splitting this integration. I'll tell you how you do this thing. You split this integration into two parts, 1 by pi minus infinity to 0 dx by 1 plus x square and plus 0 to infinity dx by 1 plus x square, and then apply the r thing that we did already. Take for example, while doing this thing, do limit of r tending to infinity, and this integral you derive from 0 to capital R. And for this one, you do r to 0 integral, you find that thing and let limit r tend to minus infinity. Either way, you can check that this integral value equal to 1. That's why the last one is also a valid example of a PDF. So these last three are valid PDFs, but the first two are not. Here we are given a particular PDF. We have seen already that e to the power this particular function is a valid PDF, and suppose the random variable capital X has this PDF. We know what is the meaning of that. In that case, let's compute these three things. Let's first compute probability of X less than 2. And by property of PDFs, we already know that that must be equal to minus infinity to 2 fx dx. And you already know the trick. You will have to split this one into two parts, minus infinity to 0 fx dx plus 0 to 2 fx dx. Look, how you should split, that will be dictated by how the function is given. Often, the way the PDF, PMF, etc. are mentioned are given values for different ranges, right? So this type of definition will tell you what should be the way to split the integration. Say here, the two ranges given for fx are minus infinity to 0, and the other part is 0 to infinity. So keeping that thing in mind, because fx is defined differently for this interval and this interval, we are splitting this integral into these two components. So apply common sense and you will know how to split it. And once you do this thing, you know this is nothing but 0 to 2, because the first part is nothing but 0. And once you are clear about this mechanism that how to split and how to go about this thing, you can directly write this thing, right? Because the intermediate steps are obvious, and then you can directly write that this is equal to this thing. Just while writing good mathematics, you should also always provide some justification. So put some justification, simple justification, either refer to the function itself or whatever. But once you are used to this kind of argument, you know that probability of x less than 2 must be equal to 0 to 2 integration of fx dx. And once we do this thing, let me write it down here, 0 to 2 e to the power minus x dx, that is nothing but minus of e to the power minus x 0 to 2, and this is minus of this thing, minus of minus e to the power minus 0. So you get uh, 1 minus this thing gives you 1 minus e to the power minus 2. So this thing is 1 minus e to the power minus 2. Now, how about this thing? We know probability of x greater than or equal to 2. This is 2 to infinity fx dx, and we can do like earlier e to the power minus x 2 to infinity, etc., etc., and you will get what it should be. However, here is a shortcut because you have already calculated how much is probability of x less than 2. These two are complementary events. One is the complement of the other. And in that case, I know that this is nothing but probability of, 1 minus probability of x less than 2. And we have already calculated probability of x less than 2. So 1 minus of 1 minus e to the power minus 2. That's why this is equal to e to the power minus 2. Can we do something like that here also? Let's check. This is minus 2 to let me rewrite this thing as, by the way, what is the event x less than or equal to 2? That is nothing but minus 2 less than or equal to x less than or equal to 2 union of x less than minus 2. I can split this event into these two disjoint events. So probability of this thing, when I take probabilities, probability of this thing can be written as probability of this plus probability of this. Now, because x is a non-negative random variable, by this time it should be obvious to you that this component must be equal to 0. If you cannot visualize it directly, then you can write it down as integration of minus infinity to minus 2 fx dx. I'm just talking about this part. And over this range, minus infinity to minus 2, fx is equal to 0. Look at this component. So that's why this is equal to 0. So this part is equal to 0, and you are left with only this component. That's why I can write that probability of minus 2 less than or equal to x less than or equal to 2 is nothing but probability of x less than or equal to 2. And you already know that is not that probability of x less than or equal to 2 is same as probability of x less than 2. Why is it so? Because capital X takes the exact value 2 with probability 0 only. And we have already computed this probability of x less than 2, and that is nothing but 1 minus e to the power minus 2. So using this, using the result of this computation, we can easily compute the other things. The other way to do it, directly use the integral property and solve the integrals that you could have done. Or in this particular example, we can use the already computed values. We have seen what are random variables and what are continuous random variables and discrete random variables. So random variables have two types, discrete and continuous. And for discrete, you have got pictures like this. Some discrete points are given and probabilities are, the probability of x is spread over these discrete points. I repeat, the probability of capital X is spread over these discrete numbers. So in between values, capital X does not assume, only takes these discrete values. And the whole probability of X, the probability of X, what do I mean by this? Probability of X being a number, that is of course equal to 1, because capital X always takes a number, numerical value. So probability of X being a number, that is always 1. And which value that is split into this, that probability is split into these discrete numbers. Now, in contrast, when you consider continuous random variable, X continuous, then it's spread over the whole line, or it may be concentrated on some regions. Say maybe here and here only there is probability, but then probability is spread over these intervals. And you cannot tell that capital X will take exactly these values, but there are some intervals over which the probability is spread out. Let's give an analogy. Suppose some points are there, point masses. And then this one has got mass M1, M2, M3, etc., Mn, either finitely many or infinitely many particles. The total mass is summation mi. However, if you are talking about a, say, rod-like structure like this thing, then you cannot say that exactly my mass is my mass, or say the probability of the I'm extremely sorry, the mass of the rod is concentrated only at these points. You cannot say that. The mass of the rod is spread all over, and that's the gist of continuous random variable. The probability is spread over a region. It's not concentrated on some discrete points. So the way it is, there it may be over the whole real number system, or it may be only on the right side of the real number system, or it may be only on the left side of the real number system, or it may be concentrated only on 0 to 1 and then 2 to 3. All these are possibilities. But then the basic difference should be clear to you, that it's not that it's concentrated only at discrete points. That's the basic difference. And you know what are the properties of these two things? So first, both of these things say that's common. And for discrete, you have got summation of fxi equal to 1. And for continuous, you have got minus infinity infinity fx dx equal to 1. And both these things, x, it may be discrete or it may be continuous. If it is discrete, you get a probability mass function. If it is continuous, you get a probability density function. And once you get this PMF or PDF, depending on whether it is discrete or continuous, your job becomes very easy, because you can calculate all different types of probabilities involving the random variable capital X. Like how much is the probability of X equal to 3, or how much is the probability of X less than or equal to 3? What is the probability that minus either X is in this interval or X is greater than 5? All these things you may be able to calculate. Of course, the computation may be complicated numerically, but theoretically it is all done. Then it is only a numerical calculation of those things. These things are extremely valuable to us, probability mass function and probability density function, because both of these things provide the probabilistic picture about the random variable capital X. So we come to the end of this session. Hope you understood the concept. In the last session, we covered discrete random variables, and here continuous random variable. Both are important, and in the subsequent sessions, those will be used. Thanks for listening.